Let's begin with a familiar concept: gravity, a force. A fundamental definition that most of us were taught from our school days. Matter attracts matter. Our Earth pulls you towards it. The moon exerts a pull on the oceans, and the sun holds the planets in their orbits. At first glance, this seems incredibly simple and easy to visualize. It's almost a self-evident truth. You drop a ball, and it falls. Of course it falls, because gravity is pulling it down. For over 300 years, this idea worked incredibly well, to the point where it became one of the most reliable descriptions of the natural world ever recorded. Isaac Newton, with his extraordinary intellect, even gifted us a formula. You multiply two masses together, divide by the square of the distance between them, then multiply by a universal constant, and you'll be able to accurately predict the motion of the planets for centuries to come. Applying that magnificent formula, scientists predicted the ocean tides and the complex orbits of comets. They even located hidden planets never before seen by human eyes. Its accuracy was so extraordinary that in the 1800s, astronomers applied Newton's laws to unveil the mystery of an entirely new planet, Neptune, simply through calculations of where an unseen gravitational force must exist. When a principle allows you to discover a planet based purely on mathematics, you're bound to place your full trust in it. Nevertheless, a strangely unbelievable truth always lurked within the concept of gravity as a force, a problem that even Newton himself pondered. Imagine a sphere hurtling towards Earth. There's no contact between the Earth and the sphere. No string connects them. No supporting rod, no physical link whatsoever. Between them is endless space, an absolute vacuum, nothing. Yet by some mysterious means, the Earth senses the sphere's presence and immediately pulls it down. What prompted it to act this way? How could an object reach out across the void, drawing another object towards it without any physical connection or transmitted signal? Newton dubbed this phenomenon action at a distance, and even his brilliant mind had to concede its inherent absurdity. Indeed, he documented that the idea of one object influencing another across empty space without any physical mechanism was so profoundly strange that no clear-thinking individual could readily accept it. Nevertheless, his formula proved astonishingly accurate. And thus, for over 2 centuries, physicists embraced and utilized it while conveniently sidestepping the question of its mysterious underlying nature. Gravity pulls, everything falls. Planets orbited, the universe seemed elegantly simple. Until one day, tiny fissures began to creep into that perfect picture. And once you perceive those fissures, an extraordinary truth will be unveiled. The force you've long believed to be holding everything together might not exist at all. For over 2 centuries, Newton's model of gravity operated almost flawlessly. The formula was simple, elegant, and achieved an almost unbelievable degree of accuracy. Simply by knowing the masses of 2 objects and the distance separating them, one could precisely calculate the strength of the gravitational attraction between them. This simple relationship explained everything, from an apple falling to the ground to the moon's orbit around Earth, and even the graceful arcs planets trace as they revolve around the sun. Engineers applied it to construct sturdy bridges and robust harbors. Astronomers relied on it to accurately predict solar and lunar eclipses decades in advance. Space agencies utilized it to launch spacecraft across billions of kilometers of the void, guiding them to fly past distant planets with absolute precision. When the Voyager probes were launched, their entire trajectories were calculated based on Newton's gravitational principles. This involved close flybys of Jupiter and Saturn. They stole a small portion of orbital kinetic energy from each planet, transforming it into a colossal slingshot maneuver to accelerate towards the distant reaches of the solar system. Every movement, every interaction was calculated with astonishing precision by Newton's formulas, and the outcomes consistently matched predictions. This was no flimsy hypothesis. On the contrary, it stood as one of the most rigorously tested and confirmed theoretical frameworks in all of scientific history. Yet perhaps the most compelling evidence of its extraordinary power emerged vividly in the 19th century. When astronomers meticulously tracked the planet Uranus, they detected a slight anomaly in its orbit. This deviation did not perfectly align with what Newton's laws had predicted. Instead of hastily concluding that the law of gravity was flawed, two mathematicians working independently arrived at a profoundly different deduction. If the orbit was perturbed, then there must be an unseen entity exerting a gravitational pull upon it. Based solely on Newton's formulas, they precisely determined the celestial coordinates of this mysterious object. In 1846, German astronomer Johann Galle pointed his telescope directly at the predicted spot. Within just 1 hour, he discovered a brand new planet, Neptune, a world that had never before graced human sight. Its existence was unveiled solely through the power of mathematics and the fundamental principle that matter possessing mass attracts other matter possessing mass. When a theory can predict the existence of a planet before anyone has observed it, our natural reaction is crystal clear. You would place absolute trust in that theoretical framework. And indeed, for a long period of history, physicists acted precisely in that manner. However, hidden beneath this string of resounding successes was a small but persistent problem constantly nagging, a tiny discrepancy between what the theory predicted and what actually occurred. This later on would force the scientific community to reevaluate the entire concept of gravity. Eventually, however, a crack began to appear. It was so small, so minuscule, that its very existence was almost surprising. In fact, its smallness made scientists wonder for many years whether it truly held significant meaning. A challenging astronomical puzzle awaited deciphering, and it concerned the planet Mercury. This tiny celestial body resides closest to the Sun in our planetary system. It is the planet with the orbit nearest to the Sun. Like its brethren, Mercury moves around the Sun in an elliptical orbit. However, that elliptical orbit is not stationary in space. Gradually, over time, this orbit shifts. Scientists call this phenomenon the precession of the perihelion. To visualize it, imagine the orbit as an ellipse drawn around the Sun. The major axis of that ellipse will slowly rotate, much like the hand of an extremely sluggish clock. In reality, this rotation is not surprising at all. It is the gravitational pull from other planets that causes these small perturbations in Mercury's orbit. What's remarkable is that Newton's formulas can calculate these perturbations with impressive accuracy. Astronomers accounted for the influences of Venus, Earth, Jupiter, and other celestial bodies in the solar system. Almost every movement of Mercury's orbit was satisfactorily explained, or so it seemed. Yet a small part remained unexplained. Even after considering all identified gravitational influences, a tiny discrepancy persisted, stubbornly refusing to vanish, specifically about 43 arcseconds per century. To help you grasp its minuteness, 1 arcsecond is equivalent to 1/3600th of a degree. An angle of 43 arcseconds spread over an entire century is a number so small it's almost unimaginable. Nevertheless, that tiny discrepancy stubbornly refused to disappear. It had persisted for decades. More sophisticated observations consistently confirmed a similar anomaly. Mercury's orbital shift deviated significantly from Newton's mechanical predictions. Initially, scientists speculated that the solution would be similar to the scenario of Neptune's discovery. Logically, if Uranus was pulled off course by an unseen planet, then Mercury must also be influenced by a hidden entity. This hypothesized celestial body was formally named Vulcan. It was imagined to orbit the Sun even closer than Mercury, hidden from view most of the time by the central star's blinding light. Astronomers diligently hunted for it for decades. They took advantage of solar eclipses, hoping the temporary darkness would reveal the mysterious planet. Expeditions were launched across continents. Some astronomers even claimed to have discovered it. But every sighting report ended in confusion. Vulcan was never found because it never existed. That reality forced physicists to confront an uncomfortable hypothesis. The anomaly wasn't due to a missing planet. Rather, perhaps the fundamental problem lay within the theoretical framework itself. Newton's law of universal gravitation, the formula that once predicted the existence of Neptune and guided science for centuries, could not fully explain Mercury's orbit. That discrepancy, though incredibly small, was an undeniable fact. And sometimes in physics, even the smallest anomalies are the key to unlocking the greatest discoveries. They are like cracks, revealing a deeper truth hidden beneath the surface of a seemingly flawless theory. The Mercury anomaly caused concern, but it wasn't yet alarming enough to signal a full-blown crisis. Scientists had faced similar anomalies in the past, and often the explanation was quite simple. A newly discovered planet, an error in measurement, or a minor correction in calculations. However, while astronomers were still diligently searching the heavens for the mythical planet Vulcan, a completely new perspective was gradually emerging, elevating the current challenge to an unprecedented level of complexity. In the early 20th century, a brilliant young mind named Albert Einstein began delving into a field that seemed entirely unrelated to gravity. His mind was captivated by the nature of light. And by 1905, Einstein had unveiled his groundbreaking work, the special theory of relativity. One of the most astonishing discoveries from that work changed everything. The speed of light wasn't merely fast. Instead, it was the absolute insurmountable speed limit in the entire universe. Absolutely no entity could achieve a velocity greater than that of light. Whether it was matter, energy, information, or any form of interaction, all had to adhere to this limit. This speed limit was not an arbitrary rule. Rather, it was woven into the fundamental fabric of the universe itself. So what did this mean for the law of gravitation that Isaac Newton had proposed? In Newton's view, the gravitational force between objects occurred instantaneously, regardless of the vast distance. Imagine, if the sun suddenly vanished, Earth would instantly perceive the absence of gravity and hurtle into space. This change, according to Newton, would occur simultaneously in every corner of the universe, with no delay whatsoever. However, Einstein asserted that this was impossible, because all information about a change could not travel faster than the speed of light. With an approximate distance of 150 million kilometers between the sun and Earth, light from our star takes 8 minutes to reach the blue planet. Therefore, if the sun were to disappear, we wouldn't know for the first 8 minutes, because its last rays of light would still be on their way to Earth. And if gravity also had to obey a similar speed limit, then Earth would continue its orbit around the sun for those 8 minutes before perceiving any change. Newton's theory of gravity was completely unable to provide a satisfactory explanation for this phenomenon. According to Newton's model, there was no concept of delay, no signal transmitted through space, and no specific mechanism to convey gravitational effects between celestial bodies. For him, gravity was simply an instantaneous phenomenon, present everywhere at once. In fact, even Isaac Newton himself once expressed his unease, not being entirely satisfied with this very idea. Even Newton had to frankly admit that the concept of objects interacting across infinite empty space without any tangible connecting medium indeed sounded incredibly absurd. Yet the predictive power of these mathematical formulas was so incredibly accurate that scientists were forced to temporarily set aside their incomprehension and persistently delve deeper into discovery. And then Einstein's groundbreaking theory once again pushed physicists to directly confront this very conundrum that seemed to have been overlooked. If indeed nothing can exceed the speed of light, then Newton's law of gravity, however great, cannot be the complete answer to the mechanism governing the entire universe. A theory that had perfectly explained planetary orbits for over 200 years now suddenly revealed its flaws, becoming incomplete. At that time, a small discrepancy in Mercury's orbit, previously dismissed as insignificant, suddenly took on a much greater meaning than anyone had ever imagined. Remarkably, Einstein did not begin his work with the direct intention of correcting Mercury's orbit. In fact, the ultimate solution to that perplexing problem arose from a very fundamental question. A question so seemingly obvious that almost no one had ever bothered to consider it deeply. Imagine you are trapped in a completely sealed box, floating in the vast emptiness of space, entirely isolated from all stars or planets. There are no windows nor any cracks through which you could glimpse the outside world. Inside this box, all objects are completely weightless. You float effortlessly in midair, and your shoes gently hover right beside you. If you gently push against one wall of the box, you will slowly glide through space until you lightly touch the opposite wall. All concepts of up or down completely vanish. Now imagine a powerful jet engine suddenly installed at the bottom of the box. It begins to propel the box upwards, maintaining a constant acceleration of approximately 9.8 meters per second squared, precisely the acceleration all objects experience near the Earth's surface. And right inside that box, a very strange phenomenon begins to unfold. You will distinctly feel a force pressing your body to the floor, making your feet firmly grip the surface. And if you drop your shoes, they will immediately fall straight down. Try throwing any object upwards. You will see it shoot up for a moment before inevitably returning to the floor. In a sealed, windowless room, all physical phenomena occur exactly as they would if you were standing firmly on our planet. No experiment, however sophisticated, could reveal whether you are under the influence of Earth's gravity or simply accelerating in a spaceship in the endless void. To an observer trapped inside, these two seemingly different scenarios are completely indistinguishable. This groundbreaking concept left a profound impression on Einstein's mind. Later, he himself exclaimed that it was the happiest thought of his life. If acceleration and gravity are truly inseparable, then perhaps gravity is not a force in the way we usually imagine it. Perhaps what we call gravity is merely a consequence of existing within an accelerating reference frame. Hidden within this fascinating thought experiment is a deeper mystery, a question that physicists have yet to fully explain. What causes all objects, regardless of mass, to fall with the same acceleration? Galileo himself demonstrated this marvel centuries ago. Try dropping a heavy stone and a light pebble from the same height, and you will be astonished to see them hit the ground at the exact same moment. Even a cannonball and a delicate feather will fall with the same acceleration as long as there's no air resistance. Within the framework of Newton's equations, this phenomenon is naturally explained. This happens because two inherently different quantities coincidentally cancel each other out. The gravitational force acting on an object is proportional to its mass. However, an object's resistance to changes in motion, also known as its inertia, also depends on that very same mass. The perfect balance between a stronger gravitational pull and greater resistance precisely cancels out, ensuring all objects accelerate according to the same rule. Yet these two forms of mass carry entirely distinct conceptual meanings. One type quantifies the extent to which gravity acts on an object. The other indicates how difficult it is to change that object's state of motion. Strangely, there's no obvious explanation for this identity. Yet experiments consistently confirm their incredible congruence with precision far beyond imagination. To Einstein's genius mind, this wasn't mere coincidence. It was a signal, a crucial hint. If gravity and acceleration are truly two sides of the same coin, then perhaps gravity itself is revealing a profound secret about the geometric structure of the universe, about space and time. As soon as Einstein began to view gravity through this entirely new lens, The implications quickly surpassed all predictions, becoming utterly astonishing. If the equivalence between gravity and acceleration is real, then every phenomenon we typically attribute to gravity would manifest whenever any object is accelerating. And from this, an incredibly bold prediction was formed. Now let's return to a familiar thought experiment. You're trapped inside a sealed box. A rocket engine is roaring, constantly propelling this box upwards with a steady acceleration. Imagine a small laser mounted on the left wall of the box, emitting a straight beam of light, cutting across the interior space and heading towards the opposite wall. To an observer standing outside, suspended in the vacuum of space, that beam of light would follow a perfectly straight path. That is the inherent nature of light. However, in the instant the light is traversing, the box itself is continuously accelerating upwards. As a result, by the time the beam finally reaches the opposite wall, that wall has moved up a small distance. But to the person inside the box, the light beam's path will no longer appear as a straight line. Instead, it will manifest as a curve bending downwards. The beam enters from a specific point on the left wall, but ends up at a slightly lower position on the right wall. Now recall Einstein's pivotal discovery. If acceleration and gravity are inseparable, then gravity must produce an identical effect. This led to a shocking conclusion. Gravity has the ability to bend the path of light. This prediction caused a major shock, because according to Newton's theory, gravity only acts on objects possessing mass. And since light has no mass, gravity, from Newton's perspective, would be entirely unable to affect it. Typically, we imagine light always following a straight trajectory, especially when passing by massive celestial bodies. However, Einstein made a groundbreaking statement. Light, when passing through a gravitational field, would no longer maintain its straightness, but would be bent. Although this distortion is incredibly subtle, almost negligible, theoretically it must exist. And this bold idea presented a golden opportunity for a scientific verification that was nothing short of perfect. In 1919, the brilliant British astronomer Arthur Eddington initiated ambitious expeditions with a single purpose: to witness a total solar eclipse. Because in that rare moment, when the moon completely obscured the sun's dazzling light, scientists could clearly observe faint stars hidden very close to the sun's corona in the sky. If Einstein's hypothesis was correct, then the sun's immense gravitational pull would bend the path of light from stars passing near it, making them appear to shift slightly from their true positions. Eddington carefully recorded images of the stars during the eclipse, then compared their positions with photographs taken previously when the sun was in a different part of the sky. And the results couldn't have been clearer. They perfectly matched Einstein's predictions. Light was indeed bent, just as his groundbreaking theory asserted. This news sent shockwaves through the global scientific community. Across newspapers worldwide, sensational headlines unanimously declared Newton's great law of gravity had officially been superseded. Einstein, from a little-known theoretical physicist, instantly shot to global fame. However, the bending of light, while spectacular, was just a small piece of the puzzle. The deeper insight hidden behind that prediction was what truly revolutionized our understanding of the universe. Gravity, according to Einstein, was not a force in the traditional sense we understood it. Instead, gravity seemed to be bending the very fabric of space itself. And, even more astonishingly, the flow of time was no exception. While the phenomenon of bent light dominated headlines and stirred public excitement, the most authentic and compelling evidence for Einstein's groundbreaking theory had quietly emerged several years earlier, and in a much more discreet, less sensational manner. Do you remember the incredible mystery surrounding Mercury's orbit? A subtle precession, a mere 43 arcseconds per century, had rendered Newton's law of gravity completely powerless to explain it. For decades, astronomers diligently searched for a missing planet, believing it would unravel this mystery. Yet the hypothetical planet Vulcan remained an illusion, never appearing. It wasn't until 1915 that the true explanation emerged. When Einstein completed his groundbreaking theory of gravity, this was the monumental work we now know as the theory of general relativity. With his new equations in hand, one of the first tests he applied was to Mercury's mysterious orbit. If this theory was correct, the curvature of space-time around the Sun would create a subtle alteration in Mercury's orbit. Due to its closer proximity to the Sun than any other planet, Mercury had to traverse the most intensely curved region of space-time in our system. As he delved into the equations, Einstein discovered something that astonished him. Remarkably, this new theory predicted that Mercury's orbit would shift by precisely 43 arcseconds per century, a figure that far exceeded anything Newton's theory could predict. This inexplicable discrepancy had baffled astronomers for over 50 years. What was remarkable was that this number wasn't an approximation. It was derived directly from the equations. It was perfectly precise. Later, Einstein recounted that the moment he saw that number, his heart pounded. In that very instant, he realized he might have found the most accurate explanation for gravity. The reason this new theory can untangle that knot is because it touches upon a profoundly central idea. For Newton, gravity was merely a mysterious force pulling objects together across infinite space. Forget the concept of a pulling force. According to Einstein, there is no mysterious gravitational force at all. Instead, massive objects simply bend the fabric of space-time. Don't think of space and time as just a static backdrop where all events unfold. In reality, they are dynamic and constantly changing. When a massive celestial body like the Sun appears, it warps the fabric of space-time in that region. Planets and other objects moving near the Sun simply follow their inherent paths, which are shaped by that curvature of space-time. Scientists call these paths geodesics. Mercury is not affected by any invisible pulling force. Instead, it simply glides along the straightest possible path through the region of space-time warped by the Sun's mass. Because this curvature near the Sun deviates slightly from what Newton had imagined, Mercury's orbit gradually shifts as it revolves around the Sun. This perspective is completely contrary to the old concept of gravity. No longer are there mysterious forces spreading throughout the universe. The movement of planets is now merely a consequence of the structure of space. Matter and energy shape the architecture of space-time, and that architecture in turn guides the movement of all objects. When we view gravity from this perspective, mysteries that seemed unsolvable in Newton's theory suddenly become clear. To fully grasp what Einstein's theory conveys, we must delve into something even more astonishing than curved space. The core effect of gravity actually lies not in the curvature of space, but in the curvature of time itself. Mass alters the rhythm of time's flow. At first glance, this might surprise you, but it's not a far-fetched idea. In fact, we have directly verified it through countless scientific experiments. Let's imagine a simple scenario. You place two perfectly accurate clocks in the same space. One rests on the floor, while the other is elevated on a stand just a few meters above the ground. And here's the marvel Einstein predicted. The clock closer to Earth will tick slightly slower than its counterpart higher up. Although this difference is incredibly tiny, its existence is an undeniable fact. In other words, where gravity is stronger, the flow of time becomes slower. This prediction was spectacularly proven in 1959 when two physicists, Robert Pound and Glenn Rebka, at Harvard University conducted a groundbreaking experiment. They meticulously measured the energy of gamma rays as they traveled up a tower approximately 22 meters high. Astonishingly, as the photons escaped Earth's gravitational field, they lost a small amount of energy, clearly demonstrating that time at the top of the tower passed slightly faster than at its base. Subsequent research and experiments have continuously reinforced and confirmed this effect with ever-increasing precision. Thus, time is not an immutable flow, Rather, it exhibits truly peculiar behavior. This isn't just an interesting phenomenon confined to laboratories. It directly impacts technologies that millions of people rely on every day. Consider the satellites of the Global Positioning System, GPS, which hover around Earth at a dizzying altitude of approximately 20,000 kilometers. At that altitude, gravity is significantly weaker than on the ground, and as a result, clocks on satellites run slightly faster than clocks we have on Earth. Each day, this difference amounts to about 38 microseconds. This number might seem tiny, but if engineers don't carefully calculate and adjust for it, the GPS system would quickly accumulate enormous errors. After just one day, your phone's location could be off by several kilometers. Therefore, your ability to accurately pinpoint your location is undeniable, living proof of the correctness of Einstein's theory. And that is the astonishing connection between time and gravity that we experience every day. Imagine this. Everything, from the tiniest dust particle to the most massive galaxy, is constantly gliding across the fabric of space-time. Even if you're sitting still, seemingly motionless, you are in fact continuously moving forward through the flow of time. Every tick of a clock, every wrinkle etched deep into our skin, is a testament to each fleeting moment. As Einstein revealed, the presence of any mass has the ability to bend and distort the very flow of time around it. The closer you are to Earth, time subtly slows down, a distinct difference compared to more distant regions of space. As a result, space-time is no longer flat. It forms an invisible slope, a distortion within its very fabric. When an object is released, it isn't being pulled. It simply follows the most natural path through that curved space-time. This path always curves, heading towards where the pace of time is slowing down. And what we witness, nothing less, is the phenomenon of falling that we commonly observe. So gravity isn't some mysterious force pulling everything down. Rather, it's simply how objects naturally move in a space where time doesn't flow uniformly, but at different rates at each point. Once you've grasped this perspective on gravity, an even more astonishing truth becomes clear. A falling object isn't being forced to move. On the contrary, it's freely gliding along the most natural path. As Einstein envisioned, objects in free fall aren't subjected to any pulling force. They are simply following the straightest possible path through a curved space-time. Physicists have named these natural paths geodesics. To make it easier to visualize, we can use a very simple analogy. Imagine two explorers setting off from the equator, steadfastly heading north without veering left or right. Each believes they are walking in a perfectly straight line on the surface they're traversing. However, because Earth is spherical, these seemingly straight paths gradually converge, drawing closer to each other as they advance further north. Inevitably, they will meet at the planet's north pole. To someone unaware of Earth's spherical shape, it might feel as if some invisible force is mysteriously pulling the two explorers together. However, in reality, no force is acting upon them. Both explorers are simply moving in a straight line on a surface that is inherently curved. Imagine that the very shape of this space has bent their paths, compelling them to meet at a single point. And a marvelous, entirely analogous phenomenon is precisely the nature of gravity. Massive celestial bodies like our planet have the ability to bend the fabric of space-time around them. When you drop a ball, it doesn't fall, it simply glides along the most natural, straightest possible trajectory within that curved space. From our perspective, it appears to be a free fall towards the ground. But in reality, the ball itself is not being acted upon by any force. If you could accompany the falling ball, you would experience a sensation of floating, complete weightlessness. And this is the secret behind the experience of astronauts. They are orbiting Earth, and surprisingly, gravity is still constantly pulling them. They don't feel their weight because they're freely gliding along the most natural trajectory through space-time. And this reveals one of the most incredible truths in modern physics. It is the person standing firmly on the ground who is actually experiencing a real force. When you stand on the floor, your body is being forced, unable to follow the natural free-fall trajectory towards the Earth's center. The floor exerts an upward force on your feet. Your bones brace against the compression. Your entire body is constantly being forced off the natural trajectory it would otherwise follow. The sensation you mistake for the pull of gravity is, in fact, the reactive force from the ground pushing you upward. In short, it is the falling object that is truly free. Meanwhile, the person standing still is constantly undergoing acceleration. When you understand gravity from this perspective, many everyday experiences will appear in a completely new light. The sensation of weight is not a sign of gravity's existence, but rather an obstruction, a disruption of its natural flow. A skydiver, plummeting through the air before their parachute opens, is actually much closer to the fundamental nature of the universe's motion than someone standing firmly on the ground. Forget the idea that gravity is a pulling force. In reality, free fall is the purest manifestation of gravity. And when we push this idea to its limits, the true nature of gravity reveals itself with overwhelming beauty and grandeur. If mass and energy can walk the fabric of space-time, then colossal celestial bodies will create regions where this distortion becomes incredibly intense. The most compelling evidence for this phenomenon is none other than black holes. As Einstein envisioned, a black hole is not merely a superdense mass with immense gravitational pull. Rather, it is a region where space-time itself is bent to such an extreme degree that all possible paths lead only inward. Once anything crosses the fateful threshold known as the event horizon, all escape routes vanish completely. Not because some mysterious force is pulling it, but because the very geometry of space-time has been utterly transformed in that region. All natural trajectories in space-time are bent directly towards the center. Even light, the fastest thing in the universe, is rendered helpless. It's not because gravity is holding it back, but simply because there are no longer any outward directions to follow. Einstein's theory also reveals another astonishing truth. Space-time is not an immutable, rigid entity. When colossal masses move or collide, they create ripples, waves that propagate across the fabric of space-time throughout the universe. And that is what we call gravitational waves. For nearly 100 years, they existed only on paper, as a purely mathematical prediction. Finding them seemed an impossible task, because the distortions they cause in space-time are incredibly tiny. However, in 2015, the LIGO Observatory made history by detecting gravitational waves for the first time, emitted from the merger of two black holes more than 1 billion light years away from us. When those ripples swept past Earth, they stretched and compressed space with an amplitude smaller than the diameter of a proton. Yet our detectors achieved extraordinary sensitivity to record such minuscule changes. The detected signal perfectly matched Einstein's predictions. Such groundbreaking discoveries clearly demonstrated how different Einstein's view of gravity was from the common knowledge we are usually taught. Discard the notion of a mysterious, invisible gravitational force pulling all objects together in space. Instead, it is mass and energy that are the key factors, shaping the very geometry of the universe. Space-time is distinctly curved around massive objects, and all objects within that curved space simply move along the most natural paths predetermined for them. What we mistakenly perceive as the pull of gravity is in reality merely a consequence of objects gliding through this warped space-time. So the next time you accidentally drop a cup or observe a stone falling freely to the ground, let's try to visualize that event from a completely new and deeper perspective. The cup wasn't being pulled down by some invisible force. It was simply following the shortest path, a geodesic, through a region of space-time whose geometric structure had been warped by Earth's immense mass. The universe doesn't pull objects, it simply bends, and everything within it is following trajectories shaped by that very curvature.